Hello, we're going live. How's it going? I'm live. Cool. Let's talk about... I got some student work that was asked for comment, so I'm gonna talk about some student work someone emailed me. Here's number 2. It's about the sum of 1 over n log n to the 1.5. Regular instructions. Figure out if it converges or diverges. Show how you know. What are we doing? We're thinking about, like, you think these log n's are usually insignificant compared to the n, so this thing should be about as big as 1 over n, and 1 over n diverges, so maybe this thing diverges too. You can say it's less than 1 over n, but sum of 1 over n is infinity, and being less than infinity doesn't mean you're still infinite. If we're trying to show, I guess, anything, less than infinity doesn't show anything. You want to be less than finite or bigger than infinite, and those are the sides that we know what you are. So instead of showing he's less than infinite, he's going to switch it to what can I show that you're bigger than. To make the thing bigger, we want to make the denominator smaller. He's making it... Wait, no, to make the fraction smaller, we want to make the denominator bigger. He's making it bigger by replacing this log n to the 1.5 with an n. The fact that any power of log n is going to be smaller than n is true, but not so true that you can, like, say that it's true without justification. Like, that's good to have the function stacked up in an organized way in your head so that you know that this is going to be bigger than that. But this is the kind of thing that's not obvious enough that you do need to show some work. Remember to turn on my music so I don't go crazy. I figured out it makes a huge difference to me. If I turn music on, I don't feel like I'm sitting in my closet, which is helpful. Okay, log n is less than n. Log n to the 1.5 is also less than n. The trouble is, you're going to end up showing that this thing is bigger than the sum of 1 over n squared. But this is finite. And being bigger than finite is the one that doesn't teach you anything. You want to show that you're bigger than infinite or smaller than finite. It turns out comparing this thing with a p-series is never going to work. Like, it is bigger than 1 over n, which is the smallest divergent p-series, but it's smaller. This thing is bigger than every convergent p-series, and it's smaller than every divergent p-series. It fits in that pocket where you can't compare it either direction. So this limit comparison thing is fine. The L'Hopital's rule is working great. Is it? I shouldn't say that without actually checking. But at this point, it's clear we're headed down a wrong track. And if this was an exam, I'd be looking for, hey, did you do anything good that I can show you? There's a step going on that you're, You want to show that this is bigger than 1. You're doing that by considering not the limit of this, but you're taking the limit of that to the 2/3. Okay, here's where the paragraph starts. We will show that this is bigger than that. F of x is the function this. Okay, the sentence is bad for 2 different ways. When you change the name of a letter in, like, the fact that f of x is here a capital F still doesn't count as making your sentence start with a capital letter. There's also the issue of f of x is this function. This is the kind of statement where, are you concluding that f of x is the function? Are you asking if f of x is the function? Or are you defining f of x to be the function? Here you're defining f of x to be the function. You should use a phrasing that makes it clear you're making a definition. The usual one is let f of x be the function, or suppose f of x is the function, or something like that. You're killing 2 birds with 1 stone, putting a word before the f of x and inflecting the sentence so that we know this is a supposition and not a conclusion. Let f of x be this function. We see by the L'Hopital's rule that this, thus, f of x to the 3/2 goes to the... Okay, you're doing this great. You see from L'Hopital's rule that this limit is plus infinity. So, f of n goes to infinity. This limit is plus infinity. In particular, it's bigger than 1, so this is bigger than this is eventually true. Awesome. This immediately gives that this diverges by direct comparison with this series. Okay, here's the place where your conclusion doesn't get to work because this converges. You showed that it's bigger than something that converges. You don't learn anything from that. But you tried it again with the integral test, which is the correct way to do it. When you're in the tiny little cracks between every convergent p-series and every divergent p-series, the integral test is the finest way to get in there. That doesn't necessarily mean you use the integral test right away. Sometimes there will be situations where you need to, like where you need to do a direct comparison to something and then use the integral test on that other something. Like, you may need to connect the dots to something that you use the integral test on. But I think the integral test is the only, at least among these tests, thing that's going to do it. You got this. So you're doing... Okay, so step 1, you're integrating this with respect to n. I think it's always going to be bad form to integrate with respect to n. Like, too much of our shorthand writing relies on that n is always an integer. If n is allowed to be fractions, then just the virtue of writing sum from n equals 1 to infinity suddenly allows... Wait, is n also going to hit 1.5 on its way to infinity? The sigma has built in that no, you only count the integers, but you really don't want to let n not be an integer. You can integrate with respect to n, there's no mathematical reason not to do it, but like math language is just not accommodating to that. This looks bad. I would just do this with respect to x. You're stating this integral, which is connected to the series, but yeah. I guess I definitely understand what you're doing. So maybe it's not that bad, but I think it's bad form to integrate something with respect to n, because you need n to be an integer, and any variable you integrate against needs to be a real variable. The integral looks like it's going right. No need to convert back to x's. Well, you should have converted to x's in the first place from n's, but yeah, it's a definite integral. Your answer is a number. You can do it from the u step. Since the functions x and log x to the 1.5 are both eventually positive and increasing, it follows that x log x to the 1.5 is increasing in positive, and that this is decreasing in positive. This all works. It feels a little bit weird to be starting from the fact that log x to the 1.5 is positive and increasing. It's true, and the reason I can look at that and know that it's true is because log x is positive and increasing. If you're starting with, we have these obvious facts, and from that we get the bigger one, I think it's more natural to me to start with log x is the basic one. X log x is eventually increasing in positive, so log x to the 1.5 is positive, is increasing in positive. So like insert one more step into here. To me is more natural, but not necessary. Follows that f of x is increasing and decreasing in positive. If you're writing f of x, then this needs to be 1 over x log x to the 1.5. Part of the reason we make a big deal about n's a whole number and x is a variable is sometimes we're talking about sequences and sometimes we're talking about functions. If you want to use the alternating series test, you need to know that the series is decreasing, that the sequence is decreasing. If you want to use the integral test, you need to know the function is decreasing. Those are separate, different requirements, and we want to make sure if the function is decreasing, that means that the sequence is decreasing. So they are connected statements, but they only go one direction. Part of the reason to use x as a variable is to make it clear we're talking about the function, not the sequence here. We need the function to be decreasing in positive, not the sequence. These collections allow us to use the integral test. Since this is a finite value of this, it follows the given series converges. Great. This is a great write-up. My suggestions are not a big deal, and I'm bringing them up because this is my chance to bring up small little comments like that. Good work. Hooray. I hope you guys are doing write-ups of these things. If you have questions if you want me to take a look at your write-up, send it in. If you want me to look at it but not do it on stream, I can do that too. Last time we talked about a bunch of series. And there's we're headed towards talking about power series, and there's two directions. Angle of attack 1 is geometric series we know. We know when they converge, we know what they converge to. So we can find the power series expansion. We did 1 over 1 minus x as our baby one. 1 over 1 minus other expressions of x squared. 1 over 1 minus negative x squared I can do. 1 over 1 minus 5x. If I get good at pulling a constant out, I can 1 over 2 minus 6x. As it turns out, if you... we didn't do an example like this. We can use a partial fraction decomposition to split something like 1 over x squared minus 6x minus 8? Does that? No. 7? Yeah, this factors. You can factor the bottom, you can do a partial fraction decomposition, and then you can write a power series for each of those partial parts, and then you can combine those together into one power series for the sum of those parts. This is another of those places where a partial fraction decomposition can do. We did natural log 1 minus x because its derivative is one of these. We did tangent inverse x. It was the derivative of this. We can find power series expansions of some functions. We can differentiate and integrate. And that gives us lots of power series expansions that we know converge to the right thing. We briefly mentioned the second angle, but we haven't gotten really far with it yet, is if you hand me a function, can we write e to the x as a power series? These functions that we've done it for are all things whose derivative or maybe integral turn into a power series that we can do. Like, that makes these doable. The function itself, if I differentiate it or integrate it in the right way, it becomes a rational function, a polynomial over a polynomial, which are the only things that a geometric series will ever converge to. Like, if you think about all these, they are a polynomial on top and a polynomial on bottom, and that's the only thing that the geometric series will ever add up to directly. It's 1 over 1 minus the thing, which is going to be some power of x, was always going to end up being a rational function. E to the x, I know all its derivatives, I know all its integrals. There's nothing I can do to turn this into a rational function. So there's no way he's ever going to be a geometric series. Like, this first angle is great because we know what it converges to, and we know when it converges. If you hand me some other function that I can't use these tricks on, I don't have the tools to do that, and that's what we're going to be aiming at today. The thing we're going to be talking about is called a Taylor polynomial. The Taylor polynomial is an attempt to take a function and write its power series. And it's the thing we did last time for e to the x. By taking its derivatives and evaluating it at 0, we made the conjecture that e to the x is maybe 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus so on and so on, with the nth term being x to the n over n factorial. It turns out that thing does equal e to the x. That is the definition of e to the x, or you could take it as the definition of e to the x. I think most complex analysis classes will say, hey, here's the definition of e to the x. And from that, you can learn that its derivative is itself and all the other things. Since we know that, yeah. But how do we know that it converges? Not how do we know that it converges. One thing we can do, whether it converges is a question we can answer. We talked about that last time. We know how to find the radius and interval of convergence. Of the right-hand side. I don't know if we did this one yesterday, but it's the type of problem that we do. The interval is always, this thing always converges. The bottom is a factorial, the top is an exponential, the bottom is much, much bigger than the top. You use the ratio test and you get that the thing converges for all real numbers. But we don't know that it converges to e to the x. So we're sort of headed towards, by the end of today, being able to show that that's true. It's a gross inequality that we use, and before we do that, we start by talking about Taylor polynomials. The idea is basically an extension of the idea of a tangent line. Here's the core idea. If I wanted to approximate the square root of 100.3, you don't need any calculus at all. To say, like, in whatever class you learned what the square root is, it's a little bigger than 10. That number is a little bit bigger than 100, so the square root of 100.3 is going to come out to be a little bit bigger than 10. No calculus necessary. And when you get to Cal 1, you know the idea of a tangent line. You can think about the function square root x. I know the derivative of that function. It's 1/2 x to the negative 1/2. Both of these things are evaluable at 10. I can find f of 100 is 10. I can find f prime of 100 is, that's supposed to be a 2. 1/2, 1 over root 100 is 1 over 20. Those two facts tell me a tangent line, which is the linearization of the function at 100. The idea being that somewhere out here at 100, if you want to move over a little bit to 100.3, when you know the slope of the tangent line, you get a pretty good estimate for how much the function is going to wiggle from 10. We already knew it was a little bit bigger than 10, thinking about a differential. If you ever talked about those dx problems, this is that kind of deal. A differential lets us say it's about this much bigger than 10. F prime of 100 is 1 over 20. The tangent line is y equals the y value plus the slope times x minus the x value. That's going to be f of 10 plus f of 100, which is 10, plus f prime of 100, x minus 100. That's the idea of a tangent line, is here 10 plus 1/20th of 100.3 minus 100. That's a 20th of 0.3 is 3 out of 10. That'll be 3 over 200. That's 1.5 over 100. That's 0.015. I need to move the decimal place back twice. It's 10.015. According to my not that difficult by hand computation, the square root of 100.3 is 10.015. Let's investigate that, because I like feeling good about getting awesome things. What's the square root of 100.3? It is 10.01, so close to 10.015. It's a tiny bit off. The thing we're getting now in Cal 2 is the ability to use higher order derivatives to improve this estimate. This is the y value. Once I know the derivative, that tells me something about how to improve that y value. If I know more derivatives, I'm able to make more good estimates. This leads to what we call the Taylor polynomial. Given a Taylor polynomial is a natural extension of the tangent line. A tangent line is the best line for approximating a function near a point. The Taylor polynomial of order 3 is the best cubic polynomial for approximating something at a point. Given a function f of x at a point, I'm going to call it x naught, the nth Taylor polynomial of f at x naught is, the idea is that it's a pretty good approximation of f of x. The name we give to it is nth Taylor polynomial of x is t sub n, is, you say f of x naught plus f prime of x naught, x minus x naught. These first two terms are just the tangent line. I'm going to need more space. The next term is going to be the second derivative over 2 factorial x minus x naught squared. And the last term will be the nth derivative at x naught over n factorial x minus x naught to the n. If I want to write a closed form expression, like these dot dot dots are a little hand wavy, I'd like a better, more complete thing. It's the sum from k equals 0 to n of take k derivatives of the function, plug in x naught, divide that by k factorial, x minus x naught to the k. And again, we're taking the convention that 0 to the 0 is 1 whenever I'm in this situation. Cool. Alright, while I'm thinking about this stupid square root of 100.3, let's check what this would do for the square root of 100.3. Like, we used Cal 1 to get an estimate of square root of 100.3 that was accurate out to 3 decimal places. Presumably, if I grab a couple more, we can get a really good estimate, right? Like, now we can grab as many as you want. Can I get infinitely many digits out of this? What would that even mean? I guess it would mean the series converges to the correct thing. Just to prove that this is useful, my function was x to the 1/2. Its derivative was 1/2 x to the negative 1/2. The second derivative will be negative 1/4 x to the negative 3/2. Maybe we can do the third one. Will be positive 3/8 x to the negative 5/2. I'll stop there. F of 100 is root 100 is 10. F prime of 100, we just did that, was 1 over 20. The second derivative at 100 is negative 1/4 times 1 over square root of 100 cubed is 1,000. And f triple prime at 100 is 3/8 1 over square root of 100 to the 5th. Square root of 100 is 10. 10 to the 5th is 3 over an 8 with 5 zeros on it. So, square root of 100.3 is about 10 plus the derivative times 100.3 minus 100 is 0.3, plus negative 1 over 4,000, that 0.3 is now squared, plus 3 over 800,000, 0.3 cubed. I see a couple things. One, these new estimates are getting smaller and smaller very fast. Both 0.3 squared is getting small really quickly, and also these denominators are getting really big. So both parts of this are getting small. Our new estimate is only changing our last estimate by a tiny little bit. That might make me think that the series, if I considered all infinitely many terms, has a good chance of converging. And it probably does, for both reasons, or agreeing with each other. If I pick a number very far from 100, if I tried to plug in 200, all of a sudden I've got a 200 squared and a 200 cubed. I don't know if it converges there anymore. I think it doesn't. Actually, I think 200 is the first place it doesn't converge. Anyway, what is this number? This is 9 over 100. If I add on this one. So this is minus 9 over 400,000. Yeah. So this is 10. Plus this one was 0.015. This is going to be minus... I guess I want to divide this by 4. 9 over 4 is 2.25 over 100,000. So take that 225 and move the decimal place back 5 times. 1, 2, 3, 4, 5. Can I subtract this in my head? 10.015 minus 0. Oh, I didn't put the decimal point. 1, 2, 3, 4, 5. 1, 2, 3, 4, 2, 2, 5. Subtract that and I get 5. 9 minus 2 is 7. 7, 9, 4, done borrowing, 1, 0, 0, 1. I'm getting that the square root of 100.3, with, now we're up to 2 pages of arithmetic, is 10.0149775. Is that what we got? 10.0149887. Did I subtract wrong? This next one is going to be so much smaller that it's no way that this term is messing up these digits. Okay, so I've made some mistake here. I'm not going to try and spend too much time figuring out what it is. I like being able to get this right, and it's super impressive that you get the exact right thing. I guess I am going to think one more second about this. Negative 1/4, 10 to the 100 to the negative 3 halves. That's going to be 1 over 1,000. Your negative 1/4. Negative 1 over 4,000. I need to multiply that by 0.3 squared. 0.3 squared is 9 over 100. 9 over 100 times 1 over 4,000 is definitely 9 over 400,000. 9 divided by 4 is 2.25. So that is 2.25 over 100,000. Yeah, I don't know what's wrong. Am I off by a factor of 2? Yeah, we got a 1.125 instead of a 2.25. So I think it should have been half of that for some reason. Did I lose track of a half somewhere? I don't know. The idea is, yes, you're getting super accurate things, although mine, I have a mistake someplace. The nth Taylor polynomial is the only polynomial of degree n which has all of its first n derivatives. Let me double check I'm doing the definition right. There's an issue about n versus n plus 1 that always messes me up. It's the nth Taylor polynomial has degree n, right? Where is the definition of T sub n? Yes, is the only polynomial of degree n which has, let's name the polynomial p of x, which has that, if you take k derivatives of t at x naught, or if you take k derivatives of p at x naught, they are the same for all k equals 0 to n. Remember, the definition of this thing is that t sub n of x is the sum from k equals 0 to n of, not p. What? You... Oh. Okay. I'm not doing great on this slide. The nth Taylor polynomial of f of x. I need to say what is the name of the function that I'm taking the polynomial of. The nth Taylor polynomial of f of x is the only polynomial p of x of degree n, which has that if you take k derivatives of p and evaluate that at x naught, or if you take k derivatives of f and evaluate that at x naught, you get the same thing for all k from 0 to n. The Taylor polynomial was defined to be, you take the kth derivative of x naught, divide it by k factorial, multiply that by x minus x naught to the k, and you add those up from k equals 0 to n. It's pretty easy to check that this is true. It's also pretty easy to check that that requirement, I'm not going to try to prove this. You just plug in some numbers and it's true. I guess I'll do one of them. If you try to plug in x naught, you get the first term will be f0 of x naught divided by 0 factorial divided by 0 to the 0, which is 1. And that's 1. You get the correct thing. Plus a bunch of terms that have 0 to a power. All of which cancel out. When you take the derivative, maybe I should write out a few terms to make it clear what's going on here. This thing is a 0th function at x naught. First derivative at x naught, x minus x naught. Second derivative at x naught, x minus x naught squared, divide that by 2. Plus there's a last term. When I take the derivative of that, this first term goes away. I get f prime of x naught. This thing goes away. The 2 comes down here and cancels with that 2. F double prime of x naught is a constant. I'm just using the power rule here. The last one has an n that's going to come out front. I'll get an n minus 1 factorial on bottom when n cancels with it. The nth derivative at x naught is a constant, x minus x naught to the n minus 1. Those factorials are there to cancel out the powers that come down from the power rule. Now when I plug in 0, I get this number, the Tn prime at x naught equals f prime at x naught. So f agreed at the point, and the derivative agrees with the derivative at the point, and all these other things will be 0. If I take a second derivative, I get 0 plus 0 plus this one will be f double prime of x naught, 1 plus dot dot dot. The next one will be the nth derivative at x naught, x minus x naught to the n minus 2, and n minus 1 falls down to cancel with that n minus 1. I'm left with n minus 2 factorial on bottom of the last term. When I try to plug in x naught, I get f double prime of x naught. T double prime of x naught equals f double prime of x naught. T prime of x naught equals f prime of x naught. T of x naught equals f of x naught. They're each taking terms being the only thing that is not 0. And when I plug in x naught into the derivative and get the non-zero, I've stacked it so that the correct thing shows up. The Taylor polynomial is the only polynomial which has all of its derivatives match up with the function. This is just like the The tangent line is I want you to hit the function at the point, and I want you to hit it with the same slope at the point. This is one step beyond that, or I guess it's n steps beyond that, where I want you to hit it with the right derivative, and I want you to hit it with the right second derivative, and maybe also with the right third derivative. And the claim is that this gives you a good approximation to f. You probably saw in some calculus class that if you have a function, I don't know how they phrase this these days. I haven't taught Cal 1 in forever. When you have a function, the tangent line is among all lines. It is the best one for approximating the function close to that point. The Taylor polynomial is in a meaningful way the best next level version of that. The best quadratic for approximating a function close to a point, assuming you're approximating it very close. How close? Even closer than that. For sufficiently closeness, this is the best possible polynomial for approximating it. It's not necessarily going to be good anywhere else, just like the tangent line usually veers away from the function. But if you're very close to that point where you're tangent, and if I could draw a tangent line, you would have the best possible approximation. All right, what we want to say is something about how good the approximation is. To do that, I don't want to try and prove the general version, because I'm really bad at teaching that. You've already seen I'm sort of flying off the rails in this lecture today. I'm going to do it with a specific example. Suppose I want to show... So, goal. Is to show something about how the nth Taylor polynomial of a function minus that function is very small. Near x naught, at least. This is going to do two things. One, it gives us a compelling reason to think that the Taylor polynomial is a good reason to approximate. But two, the Taylor polynomial is, like, by definition, it's the nth partial sum of what we're going to be calling the Taylor series. We made our conjecture that e to the x equals this series. If I stop that series after n terms, I've got the nth Taylor polynomial. I want to show that the Taylor series converges to e to the x, so I want to show that if you cut it off at some point, you're going to get a really good approximation of e to the x. I want to show that this is close to e to the x. I want to show that the difference goes to 0. That'll mean showing that the sequence of partial sums converges to the function. That'll mean that the series actually is the function, which is our earlier conjecture. So we're going to learn two things from that, and we're going to do it specifically for e to the x. And then we'll say the general statement after it. So we're going to think about the third Taylor polynomial. Nope, we're not. We're going to think about the second Taylor polynomial. And e to the x at x naught equals 0. So t2 of x is defined to be f of 0 plus f prime of 0 over 1 factorial, which is 1 doesn't do anything, x minus 0 to the 1, plus f double prime of 0 over 2 factorial, x minus 0 to the 2. We computed this last time. All the derivatives are e to the x. You plug in 0 to any of the derivatives, you always get 1. So this number and this number and this number are all 1. I get that it's 1 plus x plus 1/2 x squared is our quadratic approximation to e to the x at 0. I want to show that you're about e to the x. I'm going to let r2 of x be the difference, is e to the x, actually I'll subtract the e to the x because then I'll have to write 1 minus sign. 1 plus x minus, how do I write it? I should probably write it the correct way. No, I do it the other direction. R2 is the other way. It's f of x minus t sub n of x. This is e to the x minus 1 minus x minus 1/2 x squared. I want to figure out a way of showing that this is small. A couple key things to note. What do I get if I plug in 0? I get my function evaluated at 0 minus t2 of 0. What's r2 prime of 0? It's my function evaluated at 0 minus f prime of 0 minus t2 prime of 0. Like, these are coming from... I never wrote the definition. Yeah, it's f of x. No, don't do that. R2 is f of x minus t2 of x. So it's, when I plug in 0, I get f of 0 minus t2 of 0. When I take the derivative, when I take the second derivative, I get f that many derivatives at 0 minus t2 that many derivatives at 0. And we just observed that these are all 0. Because the whole point of t2 is it's the function whose first two derivatives, its 0th derivative, its first derivative, and its second derivative, are the same as the value and first derivative and second derivative of the function. So r2 is a function that... This r is for remainder, by the way. It's how far off is the function from t2 of x. This second level remainder is a function which equals 0 for all of its derivatives at that point. And we start by saying, how big is the third derivative? The third derivative of x is going to be f double prime of x minus the third derivative of t. Well, t is a quadratic polynomial. If you take 3 derivatives, they will all go away. So the third derivative of r3 of x, the third remainder, is just the third derivative of f. Like, these 4 facts are enough to define this remainder function. I know what its third derivative is, and I have some initial value points that I could use to figure out what r is from that. And we're kind of going to now backtrack and reconstruct r from these observations. But first I want to say, suppose that f double prime of x, this is e to the x, has that the absolute value is less than m. When is it less than m? I want to say it's less than m on some region, on the interval from minus d to d. D is going to be some distance, some radius. I can't show that e to the x is close to the polynomial everywhere. So I'm going to try and show it's close to it on some little region from negative d to d. And I'm hoping that the third derivative is not too big on this region. Or if it is big, I'm just giving a name to that bigness. I'm going to say the smallest that the third derivative of e to the x ever gets is m. I can say what my m value is here. My m value here is e to the d. The biggest that e to the x gets between negative d and d is the value it takes on the right, because it's an increasing function. So that's going to be e to the d. So I know that the third derivative of f of x in absolute values is less than m on the interval from minus d to d. I want to integrate that function from 0 to x. I need to switch letters because I'm integrating out to x. This is an inequality that's easy to work out if you've got some interval. I'm going to assume x is positive for now, although the same inequality works when x is negative. If I have a function and I have a value m, then the integral of this function is going to be less than the integral of m. I don't know if you ever stated this in Cal 1, but it's pretty obviously true from the picture. If I integrate that function from 0 to x, I'm going to get something that is at most as big as the integral from 0 to x of m. What is the integral of m from 0 to x? This right-hand side is mx. And the left-hand side is, what's the integral of the third derivative? Well, it's the second derivative. But I need to evaluate it from 0 to x. That's going to be f double prime of x minus mx is less than mx in absolute values. In this case, everything's positive. In the more general version, there'd be some absolute values everywhere. This is the thing that I mess up on. Um, why did I start? Oh no. I'm using the. I'm still bad at this, even with these. Even just doing it for e to the x, I'm still messing this up. I am not trying to talk about f. I'm trying to talk about r3. The third derivative is the same for r3 and f. But I'm now talking about r3. The reason I want to be talking about r3 is I get r3 double prime of x minus r3 double prime of 0, and that thing goes away. The thing we observed is that it's not r3. It's not r3, it's r2. I'm so bad at this. Taylor's inequality is always the worst thing I lecture every year. I just get so sloppy. Well, we'll have the statement in a box in a second. I'm not good at getting here. You need to take this fact that R3 is at most this big and integrate that fact 3 times. And it's just messy to me, integrating inequalities. I get R2 double prime is at most as big as mx. Integrate that again. Integral from 0 to x of R2 double prime of t dt is going to be less than the integral from 0 to x of mx dt, or mt dt. From the same reason. My function's less than the thing, so the inequality is going to be less than the thing. If I was left of 0, there would be 2 minus signs canceling something out. The inequality would be reversed, but also when you integrate over a negative, over a reflected integral, you get the same inequality. What is this? This is going to be R2 prime of t evaluated from 0 to x. That's R2 prime of x minus R2 prime of 0, which we just said was 0, is less than, this integral is half t squared. Evaluate that from x to 0, you get half mx squared. And do it one more time. So R2 prime of x is no bigger than 1/2 x mx squared. So integrate that from 0 to x with respect to t. R2 prime of t. That's going to be less than the integral from 0 to x of half mx, half mt squared dt. This is part of the obnoxiousness, is you want to integrate it from 0 to x. You have to keep switching the letter to t in order to integrate it. I get R2 of x minus R2 of 0. Hey, R2 of 0 we just said was 0, is at most. The integral of this thing is 1/6 mt cubed evaluated from 0 to x. That'll be 1/6 mx cubed. I'm getting that. On the interval from negative d to d, we have that R2 of x is at most as big as 1/6 md cubed. That says e to the x minus t2 of x, that was defined to be this thing, is going to be at most e to the d over 6 d cubed. We're off by something less than d cubed. If I think about what this is, like, if d is small, 0.1, then we're less than 1,000th over 6, off by this constant e to the 0.1, which is going to be closer and closer to 1 as the thing shrinks down. And this is the general type of thing for Taylor's inequality. Here's the statement of Taylor's inequality. Okay. I'm now past all the stuff that I did badly because I can just make the statement of the final thing. The way you prove Taylor's inequality is the same type of way, but you have to integrate it n times instead of 3 times, and it's gross, and I hate this proof. The Taylor's inequality says that if the function, when you take n plus 1 derivatives, I wrote that in the wrong place. The n plus 1th derivative of f is never bigger than m on the interval x minus x naught less than some diameter d. This is kind of taking the place of a delta and an epsilon delta, but I don't want to let it get all the way down to 0. I've got some specific d value in mind. Then, t sub n of x, or then if t sub n of x is the nth Taylor polynomial, of f at x naught, we have, and here's the big thing you need to write down, f of x minus t sub n of x is no bigger than m over n plus 1 factorial x minus x naught to the n plus 1. This is stronger than the thing I concluded last time. I messed this up. Yeah, this works when x goes out to d, so the same inequality happens for smaller values than d. D is the thing that's necessary for how bad does the bound ever get. But the thing I have is that you're less than x cubed because it works for every x value, which means that this difference is pinching down to 0 in such a way as smaller than a cubic. If you want the thing to be yeah, it's getting close to 0 in a way stronger than cubic. Okay, let's stop trying to go back to the pages that went bad. Here's Taylor's inequality. Here's the helpful way to remember Taylor's inequality. Remember, our Taylor's polynomial was the sum of, take the kth derivative of f, plug it in at x naught, divide it by k factorial, get x minus x naught to the k, right? The general term is kth derivative of the function, the k factorial, the difference to the k. Those three pieces are all there in Taylor's inequality. Taylor's inequality is basically saying when you add up the first n terms, you are off by at most something that's about as big as the next term, right? The next term has the exact n plus 1 factorial that would happen for the n plus 1th term. It has the x minus x value to the n plus 1, which is what would be there for the n plus 1th term. The part that's not the same is instead of what the value is at x naught, we need to say, well, how big could the value have been anywhere inside the interval? When things are continuous, which usually they are, if I take the n plus 1th derivative of x at x naught, the Taylor polynomial would have used this value. So I'm trying to sketch a graph of the n plus 1th derivative. Probably it's a continuous function, like functions are usually continuous if you can take their derivatives. The Taylor polynomial uses this value, is what would have gone on top of the fraction in the next term. The Taylor's inequality is off by a little bit. Don't use that value. Use how far off is that value if you, in the worst case scenario where you move up to d away. So how big does this get? That's m. If the thing is continuous and d is small, probably m is about the same, but maybe it's not. And there's a good chance that if you keep taking derivatives, the function gets steeper and steeper and the m gets worse and worse. This is Taylor's inequality. In general, there's a lot of stuff you do in math where you come up with a pretty good approximation. We said that the tangent line is a pretty good approximation to the function. But you probably didn't at that time go one step further to say it's so good that the difference between the function and the tangent line is this small. Saying that something is a good approximation without being able to say how good of an approximation it is kind of useless. So the idea of a Taylor polynomial is a good approximation of a function is not super helpful if you can't go the next step and say it is this good of an approximation, which is our goal here. What can we do with Taylor's inequality? There's a bunch of homework problems that are about using Taylor's inequality to say, hey, find the Taylor polynomial and say how bad this approximation is on this interval. Or say how much of an interval. There's like a lot of valves here. One, you can say that the more terms you get, this thing will probably get smaller and smaller. Although maybe m is getting bigger and bigger as you approximate that. In general, we've done enough series to know that n factorial, if n gets big faster. It's definitely going to get big faster than this thing is geometric, which is geometric. We don't know how it compares with m because m is difficult to manage. So if n is big, usually this approximation gets small. If the interval stays small, that's another thing I can do. I can say don't approximate it everywhere, just approximate it on this interval. That'll keep this thing small. That's another way of making the errors small. Let's try some examples. Let's use t3 of x to approximate e to the 2. I guess I should say for e to the x at x naught equals 1 to approximate e squared. Use Taylor's inequality. To bound your error. E to the x is the function that we know what the Taylor polynomial is right off the top of our head. T3 of x, we've written this out a few times, is going to be 1 plus x plus half x squared plus 1 more is 1/3 x cubed. Alright, and allegedly this is pretty close to e to the x. Although if you go all the way out to x equals 2, I don't feel like maybe that's not so great. Let's try t3 of 2. Is 1 plus 2 plus a half 2 squared is half of 4 plus a third of 8. It's supposed to be an approximation of e to the 2. Is it? I guess let's work this number out. This is 2. 8/3 is 2 2/3. So I've got 2, 4, 6, 7 2/3. Is 7 times 3 is 21, 22, 23 over 3. How close is this to e squared? This is our approximation of e squared. Getting an approximation that you can't say how good of an approximation it is kind of useless. Taylor's inequality lets us bound that. Taylor's inequality tells us that the difference between these, 23 over 3 minus e squared, is at most. I'm thinking about the next term. M over, we went up to the, I messed this up. It's not 3, it's 6. It's 3 factorial is what goes here. So this isn't 8 over 3, this is 8 over 6, which is 1 2/3. So it's 6 2/3, which makes this 17/3. Oh, no, this is, damn it. I'm always bad at this lecture. Okay. 1/2 2 squared plus 1/6 2 cubed. That's 1 plus 2 plus 2 plus 8 over 6 is 4 over 3. Oh, it is still just thirds if I reduce the fraction. That's 5, 6 1/3. So it's going to be 19/3. Okay. E squared is allegedly pretty close to 19/3. How good of an estimate is this? I need this m value that I'll need to figure out in a second. M is the largest. M is an upper bound of the fourth derivative of x on the interval from -2 to 2. How big does the fourth derivative get between -2 and 2? If you want to use the inequality to jump out at a distance of 2 away, then that's the window you have to use. Even if the function only gets bad up here, I still have to think about the whole thing, is the way Taylor's inequality is stated. Less than m over, not over 6, it's over the next factorial, is 24, is 4 factorial. 2 minus 0 to the 4. How big is m? What's the biggest that the fourth derivative of x gets? Well, the fourth derivative of e to the x is e to the x. How big does e to the x get from -2 to 2? It gets as big as, the biggest it gets is e to the 2. Here's the worst thing about you trying to use Taylor's inequality. This happens all the time. E squared minus 19/3 is at most e squared over 4 factorial 2 to the 4. How big is e squared? Well, that's exactly the damn question I was trying to answer. I don't know what e squared is. If I'm trying to approximate e squared, it sucks having something that I can't bound. So I need to come up with a bad bound of e squared. How big could e squared be? I can stick it into my calculator, but that kind of defeats the purpose of coming up with an approximation of e squared. It's less than 3 squared, which is 9. I know e is less than 3. How do I know e is less than 3? Well, that's the kind of thing that I could use this type of argument to. I'm just going to use my base level knowledge that e is between 2 and 3. So I've got something that's less than 9 times 2 to the 4 over 4 factorial. This is really big. What's 2 to the 4 times 9? That's 16 times 9 over 4 factorial. So I'm getting that e squared is so close to 19/3, it's within 6 away. That's not a really great approximation. I don't really expect it to be a good approximation because I went as far as 2 out. Maybe I should get one that actually shows a good approximation. Let's try. Let's estimate e to the 0.1 using t3 of x. We'll go out to 3 this. We did 3 last time. Let's do t4 this time. Find a bound on the error. With Taylor's inequality. Well, t4 of x is 1 plus x plus a half x squared plus a 6th x cubed plus 1 over 24 x to the 4. So t4 of 0.1 is going to be 1 plus 0.1 plus 0.1 squared is 1 over 100 is 1 over 200. 0.1 cubed is 1 over 1,000, so I got 1 over 6,000. 0.1 to the 4th is 10,000, so I got 1 over 24,000. I guess if I want a fraction here, I get a common denominator. You are 24,000 over 24,000. These factorials are kind of nice because they usually give you the common denominator right away. You are 2,400 over 24,000. Oh, it's not 24,000. It's supposed to be 2,400,000. Okay, so that adds a 0 here. That adds a 0 here. 24,000 over 240,000. What do I need to multiply u by? 1200. What do I need to multiply u by? Multiplying u by 4 will give me 24,000. I need to multiply u by 40 plus 1. So I'm getting 265,241. I'm not going to try and see if that reduces. I think e to the 0.1 is about this. How small is the error? The error is less than, it's going to be m over n plus 1 factorial, x minus the x value to the n plus 1. In our case, that's going to be m over 4 plus 1 is 5 factorial. The difference between the center and the point we plugged in is 0.1 to the 6. Okay, so now this part is helping us. It's making it even smaller. How big is m? M is, how big is the fifth derivative on the interval from negative 0.1 to 0.1. How big is that in absolute values? The function is e to the x. That's an increasing function. It's at its biggest on the right. So the biggest it gets is e to the 0.1. That's the 10th root of e. That's got to be less than 2. Is it definitely less than 2? It's definitely less than e, which is less than 3. That seems like the easiest bound I can get. I'm pretty sure it's less than 2. E to the 10th root of e is less than 2. That occurs if I take the 10th root of both sides and get e is less than 2 to the 10. Yeah, e is less than 1,000. So, yes, it's definitely less than 2 also. I'm going to say, if I'm writing this up for an exam, I should try to justify this inequality, since e is less than 1,000. E to the 0.1 is less than 2. I guess 1024 is 2 to the 10. So, our error is less than. That's the thing about the m, is you usually don't need that good of an estimate. The error is less than 2 over 120 times 1 over 10 to the 6. That's 1 over 60 times 10 to the 6 is 6 more zeros. Holy crap, we just got a really good estimate for the 10th root of 2. Is this right? Dear calculator, what was 265, 241, divided by 240,000. Dear calculator, what is e to the 0.1? Yep, we got 1, 2, 3, 4, 5, 6. It's out in the 7th decimal place of accuracy. Yes, this is on the order of 10 to the 7. Maybe we're off by a little more than we should be. There's a good chance I added these fractions wrong. Cool, that's Taylor's inequality. This is how I screwed up. N plus 1, n was 4. Not 4 factorial, just 4 excitedly. This should have been 0.1 to the 5 here. Our n plus 1 value is 5. I have too many zeros on there. Yeah. If I subtract these two numbers, if I take that number minus 265,241 over 240,000, it's getting my error is about this big. If I take 1 over 6 million, I get a slightly bigger than number. I am less than that error. That should have been a 5 here. That's Taylor's inequality. It's got a lot of different valves you can see it, mess with it. It's got a lot of valves you can mess with. And I have problems about those. So one of the problem is if you wanted to approximate sine x with t4 of x, and you have this specific interval, how big could the error be? This is asking you to use Taylor's inequality to say the error. 118 says, if I'm going to use Taylor's inequality, and I'm going to use that interval, but I want the error to be less than this, then how big should n be? So sort of work your way through the error term of Taylor's inequality. How big does n have to be before you know for certain that the next thing is going to be less than this small? Or if you wanted to use it to approximate this, and you need the error to be less than that, how big can the interval be? There's a bunch of different things that get smaller and smaller that you can use to manage the error. So one of them has this part and this part fixed. How small can the interval be until you're in that range? There comes a point in most of these where you need to make an estimate on how big does the function get. You want to replace that with a simple value. Here, knowing that it's less than e to the 0.1, it's kind of useless if I don't know what e to the 0.1 is, so I just said it's less than 2. E to the 0.1 is 1 point something. So jumping that up to 2 is maybe doubling the error in worst case scenario. Doubling the error is not that big a deal. Like, if I used that it was less than 1 over 60,000, but really it's 1 over 30,000. Like, it's the number of digits that we really care about, not what the value is after that many digits. Okay, that's Taylor's inequality problems. Let's try using the Taylor's inequality to show that the Taylor's. Okay, let's talk about the Taylor series. We haven't used that word yet. The Taylor series for f of x at x naught is just the limit of the Taylor polynomials. It's the sum where you go out forever. I guess I'll use k because that's what I used for the polynomial. It's the sum from k equals 0 to infinity. Take k derivatives of the function, evaluate them at that point, divide that by k factorial, multiply by x minus x naught to the k. We haven't had the x minus x naught issue going on with the e to the x, because so far we've been doing these at 0. Usually, sticking in the minus x naught doesn't really add in any extra work, but sometimes it's a hassle, so I'll make sure and do some like that soon. This is the Taylor series for a function, and it's defined whenever the series converges. Okay, here is an unfortunate fact. There are functions that the Taylor series exists and it converges, but it doesn't converge to the function. Let me say this right now. Warning. Sometimes the Taylor series doesn't converge. To f of x. That happens in two ways. Sometimes it just doesn't converge. But sometimes it converges, but it converges to the wrong thing. If we were doing the Maple Lab part of this, I have like a Maple project that's about investigating a function that has that property. I guess I can write down. No, I'm not going to spend too much time on that. Just a heads up. Like, we spend a lot of time talking about the Taylor series in the abstract. The Taylor series is not always the same as the function. We will often treat them as we want to be careful not to treat them as interchangeable. But we can claim the Taylor series for e to the x does converge to e to the x. Does equal its Taylor series. Everywhere. Pick an A. We want to show that e to the a equals the sum from n equals 0 to infinity. I guess Taylor series at x naught equals 0 is one of the things we should have said. 1 over n factorial x to the n. 1 over n factorial a to the n. We want to show that f of a is the Taylor series at a. I like using t infinity to represent the Taylor series. T sub n is take n terms of the series to get the nth Taylor polynomial. For the series, you want to use all infinity of the terms. So n equals 0 to infinity, 1 over n factorial a to the n. We want to show that. So the right-hand side is defined to be the limit as n goes to infinity of the sum from k equals 0 to n, 1 over k factorial x to the n. Taylor's inequality says that e to the a minus the sum from k equals 0 to n, a to the n over k factorial is in absolute values at most m over n plus 1 factorial a to the n plus 1, where m is how big is the function at that point. The biggest the value that gets, the biggest e to the x gets on the interval from minus a to a, or minus absolute value a to absolute value a, is e to the absolute value a. If I'm doing a specific estimate, this is not a good number to use. I would want to say how big is e to the a. This is like an abstract thing, where I know it is some number. The point is that it's constant. And it's easy to check that the limit as n goes to infinity of a to the n plus 1 over n plus 1 factorial, even with that constant of e to the a, is 0. So the series converges to e to the a for any particular a value. Which is exactly what we wanted to say. The limit of the Taylor series, of the Taylor polynomial, is the Taylor series does converge to e to the x. And this works for lots of series. You want to know a bunch of Taylor series off the top of your head, or a few of them. I guess a little bit more notation. The Taylor series centered at x naught equals 0 is called the Maclaurin series. And I believe I have this right, that the Maclaurin series doesn't have a capital L there. Although I don't know how you get your name attached to just use 0. This feels like a weird thing to have its own name. And the same for the polynomial. You can talk about a Maclaurin polynomial also. Maclaurin is just the fancy name for Taylor with 0 as the point you're centered around. So that Taylor series for e to the x we were doing was actually the Maclaurin series the whole time. I don't know why this gets its own name, but it does. We want to be able to work out some of these. Let's try sine x. derivative is cosine. Next derivative is negative sine. Next derivative is negative cosine. Next derivative is sine again. So if I think about what are these values at 0, I get the sequence 0, 1, 0, negative 1. 0, 1, 0, negative 1. That sequence is easy to understand. So the Taylor series for sine x or I guess we should call it the Maclaurin series I just said. Zero times is the constant term, plus 1 over 1 factorial x to the 1, plus 0 over 2 factorial x squared, plus negative 1 over 3 factorial x to the 3, 0 over 4 factorial x to the 4, positive 1 over 5 factorial x to the 5, 0 over 6 factorial x to the 6, negative 1 over 7 factorial x to the 7. If we throw away all the zeros, we get x minus x cubed over 6 plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus ... We have a power series that only uses odd terms. The normal way to express that is as a sum from n equals 0 to infinity. You don't use every power of x, you just use x to the 2n plus 1 is the easy way to, like, when you plug in 1 you get 1, when you plug in 2 you get 3, like this formula spits out the odd numbers. There's a minus 1 to the n, and there's a 2n plus 1 factorial on bottom. This is the Taylor series for sine x, and we're not going to go through the same argument, but it's pretty easy to imagine how, like, this is the exact same type of argument you're going to get. You just need to know that the nth derivative doesn't get too big. Well, the nth derivative of sine x never gets bigger than 1, because it's going to be sine or cosine, plus or minus. That never gets bigger than 1 in absolute value. So this one will, I guess, maybe converge even faster. How about cosine x? Let's start writing these out. Maclaurin series to know off the top of your head. Maclaurin series to know by heart. Sum of x to the n is 1 over 1 minus x. That was the first one, is basically a geometric series. The sum of 0 to infinity, 1 over n factorial x to the n comes out to be e to the x. If you have 1 over 2n plus 1 factorial x to the 2n plus 1, if you only use even terms and make them alternate, you get sine x. If you only use even terms, so instead of 2n plus 1 you use 2n, this turns out to be cosine x. E to the x is 1 plus x plus half x squared, 1 over 6x cubed, ... This one is 1 plus x squared plus x cubed plus ... This one is 1, no, this one starts with x. Minus x cubed over 6 plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus ... This is the one that uses only evens. 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus ... Any other ones to know? A lot of books will put tangent inverse. I never have the tangent inverse one memorized, but you can take the derivative of tangent inverse. We did this last time. It's 1 over 1 plus x squared. It's 1 over 1 minus negative x squared. That's a sum of negative x squared. So you get the sum of negative 1 to the n, x to the 2n. Well, the integral of that will be x to the 2n plus 1. Divide that by 2n plus 1, negative 1 to the n. Have I got that right? Let me write out the first few terms and see if they're right. When n is 0, I get x to the 1 divided by 1, negative 1 to the 1. Okay, this is not right, because when I plug n equals 0, I get negative. It should be negative 1 to the n plus 1. It's the opposite of that. Can I see why that is here? Nope, n is 0. That's right, it is negative 1 to the n. When you plug in negative 1 to the 0 is 1. Okay, so it's x. It's alternating. This is going to give a minus x cubed over 5. X cubed over 3. Plus x to the 5 over 5. Minus x to the 7 over 7. Plus dot dot dot. This one converges to it on the interval from minus 1 to 1. This converges to tangent inverse on the interval from... When does this converge? It's minus 1 to 1, right? Yes. It might converge at the endpoints. When you plug in... Oh, actually... I always get these endpoint ones wrong. This one does converge at x equals 1. At x equals 1, you get something like an alternating harmonic series converges. It doesn't converge at negative 1. Okay. It might be worth noting that now you've got a million different ways of evaluating some numbers. Like, here are a few Maclaurin series worth knowing by heart. You can do all sorts of cool things with these. Why don't I start with what's the type of thing you're asked to do in the homework? One of the things you can do with polynomials is you can FOIL them out. If you know the Taylor series for some things, you can write down the Taylor series for other junk. For example, give me a Maclaurin series for x squared sine of x to the 5th. Well, I can manipulate the one I know for sine x. Sine x was the sum of negative 1 to the n, 2n plus 1 factorial, x to the 2n plus 1. So, sine of x to the 5th is going to be, take that and replace the x with an x to the 5th. X to the 5th to the 2n plus 1. This is a sum of minus 1 to the n, 2n plus 1 factorial, x to the 10n plus 5. So x squared sine x to the 5th is another thing you can do by sticking an x squared on the outside of that. Sticking an x squared on the outside is cheating because it doesn't count as a power series anymore. But if I push the x squared in, x squared times this will be x to the 10n plus 7. That's a kind of a cool trick you can do. If you know the series, then you automatically know you can plug stuff into the series and this. Because we know sine x, this equals this for every where the same thing goes to tell us that this power series does converge to that function. Like this equal sign works the whole way down. So I know it actually does equal the series, not just that. If I ever wanted to know, like here's an example, find the 17th derivative of x of, or hang on, if f of x is x squared sine of x to the 5th, find the 17th derivative of that function at 0. Well, that's a number that appears in the Maclaurin series. I can write out the first few terms of this and just read off what is the 17th coefficient. When I plug in n equals 0, I get 1 over 1 factorial x to the 7 minus 1 over, now n is 2, 2 times 2 plus 1 is 5 factorial x to the 17, plus the next one will be an x to the 27 with a 7 factorial here. Well, this term must be the 17th term. That's going to be the 17th derivative of the function at 0 divided by 17 factorial x to the 17. Knowing that this term must match the shape of the 17th term of the Taylor polynomial tells me that I can, like, this thing equals 1 over 5 factorial x to the 17. That cancels. Multiply by 17 factorial. I learned that thus, oh, that should be a minus there. F to the 17th power of 0 is going to be negative 17 factorial over 5 factorial. Huh. Weird. Note that you don't want to take the derivative of that 17 times. It's going to be a crazy power rule whatever. But somehow the answer is going to end up being negative 17 factorial over 5 factorial. Because the power series includes information about the derivatives, using a power series is often a better way to get information about the derivatives than just taking derivatives. Taking derivatives is rough. These power series compress a lot of information in them all right away. What other homework stuff have I got that we haven't done examples of yet? Yeah, you can use known series. Let's try this. Let's find the first. Oh, fact. Fact. I'm not using the word theorem because I'm not going to try and prove it. But if the sum of an x minus x value to the n and the sum of bn x minus x value to the n both converge in an interval, let's call this one f of x and let's call that g of x, then the power series suggested by foiling these which I could write a formula down for, but I'm not going to. By foiling those two things, the sum of an x minus x naught to the n times the sum of bn x minus x naught to the n does converge to f of x g of x on the inside of that interval. If they both converge in a region, then the product converges, at least on the inside of the region. Not necessarily the endpoints. You never get the endpoints for free. The endpoints, if they converge, they do converge to the right thing, but the endpoints have chances to not converge from all sorts of goofy reasons. So, for example, I probably wouldn't want to write down the general power series, but I can find the first four terms of the Maclaurin series. I capitalized the L in Maclaurin. You're not supposed to do that. Maclaurin series of, let's make it e to the 3x times cosine of x squared. The idea being, if I can find a series for this, and I can find a series for this, like those are both going to be polynomials. When you FOIL a polynomial, you should get a polynomial. It becomes sketchy trying to FOIL infinitely long polynomials, but the key thing is, if I look for what are all the terms that give me an x cubed, there's only so many ways you can use an x cubed. If I'm just trying to find what is the x cubed, what are all the x cubed terms to group together, there's only going to be finitely many. Maybe it was x to the 0 times an x cubed, maybe it was x to the 1 times an x squared. There's only so many possibilities I have to go through to make sure I have all of the x cubed terms. The key thing is going to be writing out these things correctly. Okay, so let's start with what's e to the x. E to the x is the sum of x to the n over n factorial. Cosine x is going to be the sum of x to the 2n over 2n factorial with a negative 1 to the n. Those are the two series that I have memorized. This tells me that e to the 3x is replace the x with a 3x to the n over n factorial. This is the sum of 3 to the n over n factorial x to the n. While cosine of x squared is going to be the sum of, plug in an x squared for x, negative 1 to the n x squared to the 2n, 2n factorial. This is the sum from n equals 0 to infinity, negative 1 to the n over 2n factorial x to the 4n. So e to the 3x times cosine x squared, these both converge everywhere, so their product will converge everywhere. The statement of that fact we just made is if you converge in an interval, the result will converge inside the interval. There's no endpoints that it fails to converge at here. This thing times this thing will be, instead of writing the series, I'm going to write out the first several terms. The n equals 0 term here gives me 3 to the 0 over 0 factorial is 1. Plus the n equals 1 term gives me 3 over 1 x. N equals 2 gives me 9 over 2 x squared. N equals 3 gives me 3 to the 3 is 27 over 3 factorial is 6 x cubed. Plus, how many terms do I need? I want the first 4 terms. I've already got the first 4 terms, so cool. Hey, it's worth keeping in mind. There's a thing that gets really confusing. I probably should have made this up before. When I say the first 4 terms, you're going to be tempted to say, aha, that is the 4th Taylor polynomial. It is not. When I take 4 terms, I only reach the x cubed term, because they start at 0. The first 4 terms includes the 0th term, which means I'm going to get t3 of x. Or maybe it would be m3 for Maclaurin series, but I haven't seen people use that abbreviation. There's the Maclaurin series for e to the 3x, or at least the first 4 terms of it. For cosine x squared, if I take the first 4 terms of this, I will get, what do I get when I plug in n equals 0? I'm going to get x to the 0, this will be the constant term. 1 over 1, I get 1. The next term will be negative because of the minus 1 to the n. I'm dividing by, the top is going to be negative 1, the bottom is going to be 2 times 1 is 2 factorial is 2, x to the 4. Plus the next term will be plus 1 over 2 times 3 is 6 factorial, x to the... Wait, this is not n equals 3, this is n equals 2 still. 2 times 2 is 4 factorial. I know 4 factorial, it's 24, x to the 8. I'll stop at that point. I haven't gotten 4 terms, but I have enough that Well, you'll see. What happens when I FOIL this out? 1 times 1 gives me 1, and that's the only way to get a constant, is by constant times constant. How can I get an x? X times 1 gives me an x to the 1. 1 times x would, but there's no x term to multiply by. There's no way to multiply any other way to get an x term. So my x term will be 3x times 1 is 3x. How many ways can I get x squared? Well, I have x squared times 1, and that's it. 9 over 2x squared. How many ways can I get x cubed? Well, I've got this, and that's it. 27 over 6 x cubed. The thing I'm looking for is, what are the ways for me to multiply one of these by one of these to get an x squared? 1 times an x squared would do it, there's no x squared there. X times an x cubed would do it, there's no x cubed there. X squared times 1 would do it, there is a that there, I put it. X cubed times x would do it, there's no x there. Okay, I hope this is clear what I'm doing. I guess the next one will make it more clear, because that's the first time where there's multiple terms. What ways can I get an x to the 4th? There's 2 ways. 1 times negative 1/2 x to the 4th. And then the x to the 4th term here, which I didn't write because I said only find 4 terms. I'm going out to the 5th term because the 4th one was not a great example. The next one is 3 to the 4 is 81 over 24 x to the 4. So the 2 ways to get an x to the 4 term are this times this gives me a multiple of negative 1/2. This times this gives me positive 81 over 24. So these are the first several terms of e to the 3x cosine x squared. If I add these together and then multiply by 4 factorial, that will give me the 4th derivative of this function at 0. Being able to read off those terms on the right gives me specific information about the derivatives of the things on the left. I feel like I should do one more. So I didn't find the first 4 terms, I found the first 5 terms, because that was the first place where they interacted with each other. Let's find 3 terms of the Maclaurin series. Let's make it e to the x over 1 minus 2x. If someone writes that, you need to interpret that's e to the x times 1 over 1 minus 2x. E to the x I know, it's the sum of x to the n over n factorial. 1 over 1 minus 2x is 1 over 1 minus something is the sum of something to the n. Is the sum of 2 to the n x to the n. So their product, e to the x times 1 over 1 minus 2x, is going to be, I need 3 terms, so I'll do 3 terms of each. When there's no zeros, this is easier to understand. 1 plus 1/2 x plus 1/6 x cubed plus 1 over 24 x to the 4. I went past the place I needed to. The first several terms of this are going to be 1, 2x, 4x squared, 8x cubed. Cool. Let's try and FOIL this out. How do I get a constant term? This product is, so when you FOIL it, it's this times each of these, plus this times each of these, plus this times each of these. We can't do them in that order, because that'll have infinitely many terms of this before I even get to this. Instead of doing them in that order, we group them by what is the power of x you're going to end up with. The constant term times the constant term gives me 1 is the only way to get a constant. How many ways can I get an x? Well, 1 times 2x would do it, and 1/2 x times 1 would do it. That'll give me 2x plus 1/2 x. I'm going to scoot this down so I can draw my loopy arrows a little bigger. How many ways can I get an x squared? In the worst case, there are going to be 3. Often some of these don't happen because they're 0. 1 times 4x squared is 4x squared. Half x times 2x is 1x squared. 1/6 x... Oh, wait. Oh. I missed a term. I can't stop screwing up today. Okay. I wrote this wrong. I'm going to use green to put my corrections. I missed a term of e to the x. E to the x is 1 plus x plus half x squared plus a 6th x cubed plus... Now we've gone further than we need to. Alright, let's try this again. Constant times constant, only one way to do it. How can I get an x? I can have the 1 times the 2x. I can have the x times the 1. That gives me 2x and 1x. Which products are going to give me an x squared? I can have 1 times 4x squared will give me 4x squared. X times 2x will give me 2x squared. Half x squared times 1 will give me half x squared. Those are the only three ways to get an x squared. If I go any further here, I have an x cubed, nothing works. If I go any further here, I have an x cubed, nothing on the other side will work. And those are the first four terms. This is the third Maclaurin polynomial. There's other ways of phrasing this. If you ask me to find what's the second derivative of that function at 0, well, it's going to be f double prime of 0 over 2 factorial must be 6.5. Double both sides, f double prime of 0 is 13. I get that without actually taking two derivatives of that function, which I wouldn't want to actually take. So that's some of the cool manipulating you can do with Maclaurin series. Here's a thing that's not really relevant to your homework, but I feel like it's fun to point out. You know the Fibonacci... What's the cooler thing to point out? There's a ton of cool things I can show off now that you know the idea of a Taylor series. Let's try the Fibonacci one. You heard of the Fibonacci sequence? It's I guess I used it at least once. You take the previous term plus the term before it, and that's the new term, and it starts with two ones, so 1, 1, 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8, 8 plus 5 is 13, 13 plus 8 is 21. For no particular reason, let's consider a power series that uses those. 0 to infinity, fn, x to the n. So just stick some powers of x. 1 plus x plus 2x squared plus 3x cubed plus 5x to the fourth plus 8x to the fifth plus ... What is this? Can we come up with a formula for this function? If we could, we might be able to understand some things about the Fibonacci sequence. We might have a function that, when I take its derivatives, it behaves like the Fibonacci sequence or something. Let's assume that this does exist, and let's call it g of x. A cool thing to understand is how multiplying something by x just amounts to shifting the terms of the sequence along. This is a sequence you might want to understand is, what do you get if you shift all the terms of the sequence over? The thing you're doing to the function is multiplying the function by x. If I multiply these terms by x, I will get 0, plus this times x will be x, this times x will be x squared, this times x will be 2x cubed, this times x will be 3x to the fourth, this times x will be 5x to the fifth, right? And if I wanted to shift it over again, I would get x squared g of x. This will be 0 plus 0 this time, and now we get 1x squared, 1x cubed. Put some 1s over here. The next term in the sequence is 2x to the fourth. The next term in the sequence is 3x to the fifth. The next term in the sequence is 5x to the sixth. And the fact that the Fibonacci sequence has this relation gives us a cute way to eliminate these things. This is sort of like that elimination thing you do when you're trying to solve a system of equations, but we get it infinitely many. When I take this row plus this row, I get that row, right? What do I get when I add x squared g of x plus x g of x? I'm getting 5 plus 8 is 13. 3 plus 5 is 8. 2 plus 3 is 5. 1 plus 2 is 3. 1 plus 1 is 2. 0 plus 1 is 1. Uh-oh, wait a minute. I'm not getting the right thing here. I'm getting almost the right thing for g of x, except this first term didn't follow the same rule. I'm getting g of x, except I'm missing the first term. I'm getting g of x minus 1. Well, hey, this is a thing I can solve. This is an equation about g of x that's totally solvable. If I move the 1 to this side and the g of x stuff to the other side, what's better to move over? Let's move the g of x to the other side. I get that negative 1 equals x squared g of x plus x g of x minus g of x. Factor that g of x out, I get g of x times x squared plus x minus 1 equals negative 1. I get g of x equals negative 1 over x squared plus x minus 1. If you ever wanted to come up with a formula for the nth term of the Fibonacci sequence, which is the type of thing you often do in a discrete math class, here's sort of a back way to do it. If you can factor the denominator, which is a pain, it involves the number theta, the golden ratio. Like, this thing does have solutions that you need the quadratic formula for, but you can in the abstract factor it, which means in the abstract you can take a partial fraction decomposition of this, but the a and the b are going to be pretty gross numbers when you do it. Those are things that you can break down into power series, like we did for 1 over 1 minus x as a power series. 1 over 2 minus x is a power series. You can come up with a power series expansion for that. Those two power series expansion will combine to give you something that must equal this. So, yeah, there's a cool thing you can do. Let me double check the homework real quick. I'm sort of going on tangents here, and I think they are fun tangents to go on because once you can do this stuff, yeah, we've got everything you need to do all the rest of the homework. I'll probably need to hit some more examples. So yeah, homework 1 through 137. Is what exam 2 was over. Last time I said you can do the homework, but I had to eliminate some problems because I guess last time I taught this, I talked about Taylor polynomials before we talked about more abstract power series. Find a Taylor polynomial. Find some Taylor polynomials. So these are a pain because I'm asking you to do the Taylor polynomial at not 0. You probably have to take some derivatives directly and plug in some points. Boom, boom, boom. Use Taylor's inequality to do this stuff. Here's a power series. Find the radius and interval of convergence. That's use the ratio test and root test. Find a Taylor series for this at that point using known Taylor series. So take the Taylor series for e to the 4x and plug in 4x. Yeah. Yeah, we've hit all this stuff. The thing I want to show you... So I'm done with lecture for exam 2. We've hit all this stuff. I will do some more problems tomorrow. In particular, if there's anything on the homework that you're finding difficult, hit me up. I can come back and do some more over the weekend. Last time, I went through and did examples of all those problems. I feel dumb doing that, because if you want to just see solutions to problems, you've got a book full of problems for solutions to. Though on the other hand, I guess I want you to be able to get some sense of whether your work is right. I don't know whether this is a thing worth doing. I'll probably do that over the weekend soon. Here's the cool idea I want to show you. Hey, you know that e to the x We just said that e to the x is the sum from n equals 0 to infinity, x to the n over n factorial. This is an idea. This is a definition for e to the x. That only uses adding and multiplying. Powers of x. There are times that you might want to think about, well, what does e to the something mean? And the whole definition of e to the being multiply a bunch of copies of e together that many times doesn't make sense, but this idea does make sense. For example, the number I. I don't know what it means to take I copies of e and multiply them together, but I sure can do this for I. We haven't defined what it means to take a limit of complex numbers, but you could make a reasonable guess what that should mean. If you have a matrix, e to the matrix 2015, what on earth would that be defined to be? The idea of taking a matrix number of copies of e doesn't make any sense at all, but a matrix is a thing that you know how to multiply. If you know how to multiply matrices, I can cube them. I can stick a 1 over 6 factorial on it. I can add up these terms. E to the something suddenly makes a lot of weird sense. Let's try e to the I. I'm not going to do the matrix one because you don't learn that much from it. But if you ask, hey, what's e to the I? And instead of doing it just for I, I'm going to do it for it because that turns out to be more useful. We can let t equal 1 if we want e to the I in particular. This should be 1 plus it plus half it squared plus a sixth it cubed, 1 over 24 it to the fourth plus ... What is this? Well, these powers of I are evaluable. I squared is -1. I cubed is -I. I to the fourth is 1. I to the fifth is I. I to the sixth is -1. I to the 7 is -I. I to the 8 is 1. How do I understand what this number is? Well, the thing you do when you're talking about complex numbers is every complex number is a real number plus an imaginary part. You group the i's together and you group the real parts together. If I group just the real parts of this together, I get 1 minus half t squared. I forgot to write the t to the 4 here. Plus 1 over 24 t to the 4 minus 1 over 6 factorial t to the 6 plus ... And which parts of this have an I on it? Factor the I out of all of those. I get a t minus a sixth t cubed plus 1 over 4, 3 factorial, the next one is 5 factorial. T to the 5i minus 1 over 7 factorial t to the 7i plus ... You should recognize these. We just talked about these on the other page. This is cosine t. This is sine t. E to the I theta turns out to be cosine theta plus I sine theta. Maybe you saw this in a pre-calc class. This is how do you take an e to the complex number. If you wanted to know what that would be from a naive perspective, like if you had never seen, this is, what is this, Gauss's formula? Like there's some name for this, but like it's too routine to still get its name used because it's so basic. If you wanted to guess what e to the I something would be, the power series is a great place to start. And this turns out to be the correct answer. There's a variation on this, or when you plug in theta equals pi, you get e to the I pi equals cosine pi. Cosine pi is -1 plus sine pi is 0i. So e to the I pi is -1. Someone, I think Euler, said e to the I pi plus 1 equals 0 is an especially beautiful equation because it has every number in it once. These are the important numbers. We got a plus, we got a times, we got a to the, we got an equals, we got a 0 and a 1 and an e and an I and a pi. And it's also a cool equation because it's completely inscrutable. If you didn't do the last page of math, this looks like someone just making stuff up, but it turns out to be true. A lot of dorks get this tattooed. This is a popular dorky tattoo to get. I guess a lot of is maybe pushing it, but I have met more than one person who had that tattooed on their body, who was psyched about math. I'm going to do one even cooler. You're welcome to turn off the video here. This is like total mind-warping territory. I want to consider, what do you get when you take e to the derivative? I'm going to take e to the, just like with e to the I, I was able to figure out what e to the I should be by using powers of I. I want to think about what e to the concept of a derivative is. And just like with the I one, you might as well stick a constant in front of it because you learn more from having the extra real constant outside there. So here h is a real number. D is the derivative with respect to x, is the derivative, the idea of the derivative itself. What do you get when you take e to the derivative? What? Can this possibly make sense? Well, the derivative is something I can raise to a power. D squared would be derivative times derivative, means derivative of the derivative. If I want to take e to the derivative of something, the derivative is something I do to a function. To understand what e to the hd is, I want to apply it to a function, and it will give me a function. To apply the e to the derivative of that function, my answer, so e to the hd should be like d. This is something we do to a function and get a function. It's a function that moves functions to functions. So that's what e to the hd should be. So when I ask what e to the hd of something is, the type of thing I should be plugging into the hd is a function. Well, when the output of this should be a function. Be a real function. To understand what this is, e to the hd f, I plug a number into that function. This should be a number. Okay. So there's going to be 3 steps to this. I'm going to need to figure out what is e to the hd itself. I need to figure out what do I get when I stick a function into there. And then I need to figure out what do I get when I stick a number into that function. Let's try this out. E to the hd should be the sum from n equals 1 to infinity and a 0 to infinity, hd to the n over n factorial. This should be 1 plus hd plus h squared d squared over 2 plus 1/6 h cubed d cubed plus ... Okay, the 1 is a little bit suspicious. You got to keep in mind that 1, like the origin here, is this is d to the 0. D to the 0 means take 0 derivatives. When I take e to the hd of a function, I do all of these things to a function, take 0 derivatives of the function. H times take 1 derivative of the function. Half h squared take 2 derivatives of the function. a sixth h cubed. Take 3 derivatives of the function. Okay, that's like a sum of a bunch of functions. That makes sense. When I take e to the hd f at x, I get f of x plus h f prime of x plus half h squared f double prime of x, a sixth h cubed f triple prime of x. This is familiar, but instead of doing it at the number x, we've been usually doing it at x naught. And instead of x, instead of an h there, we usually had an x there. This is the Maclaurin series of a function. F of x naught plus f prime of x naught is the constant out front. This is over 0 factorial, this is over 1 factorial. They're not written because they don't exist. Times h. This is f double prime of x naught over 2 factorial h squared. What? So, what's the simplest way to write this? We're not quite at the Maclaurin series yet because we would need to translate it by something. Let's see. If I replace the h with an h minus x naught on both sides, so I've just learned that e to the hd f at x naught is supposed to be f of x naught over 0 factorial, f prime of x naught over 1 factorial times h, f double prime of x naught over 2 factorial h squared plus dot dot dot. If I want to make this all the way into the regular old Taylor series, I want to replace h with x minus x naught. I want to change h into x minus x naught on both sides. E to the x minus x naught d f of x naught is going to be f of x naught plus f prime of x naught, x minus x naught to the 1, plus f double prime of x naught, x minus x naught squared, dot dot dot. This one's got the 2 on it. This is exactly the Maclaurin series, the Taylor series, for f at x naught. That's the thing that maybe equals f of x minus x naught. No, equals f of x. And now what do? I want to replace x naught with x plus t. Let's let x equal t plus x naught. I get f of t plus x naught on the right, and on the left I get x minus x naught is t. I get e to the td f of x naught. So I translated it to make it look like the Taylor series, and then I translated it back. It turns out e to the t d turns out to be, when the Taylor series converges, it comes out to be the idea of translating to the function to the left by t. If I replace these x naughts now. The new function I get when I replace f with e to the t df is the translation of f by t. What? So e to the derivative is translation left by 1. Those are both things you can do to a function. You can translate a function to the left by 1, you can take the derivative of a function. E to the derivative is translation by 1. There's a cool equation to have worked out. What does that mean? I don't know. I just love it though. I just love thinking about the idea of e to the derivative means translation. Weird. That's the idea of Taylor series. Start getting ready for the exam. Do all the homework if you haven't done the homework. If you have questions on the homework, you can mail them to me. Some point tomorrow, I might do it early and do it tonight. I'm going to go through the practice exam. Feel free to take the practice exam in a quiet room. Come back and see how you did on it. At some point, if I can get the motivation together, I need to... Yeah, I'll probably do that soon. Maybe tomorrow. I'll sit down and go through the odd homework problems. Maybe that'll be all I do tomorrow, is do a bunch of odd homework problems. Maybe not all the odds, maybe just the multiples of 4 or something. I'll go through the practice exam, I'll do a bunch of homework problems. Hopefully, I want to do some homework problems so you have some solutions to look at, but I feel dumb doing your homework for you. Like, I don't want you looking at that video until you've actually done the homework, is the point. Like, you don't learn anything watching someone do. I had a good math teacher who explained to me that taking a math class is like taking a bicycle riding class. If you go into the lecture hall and watch me ride a bicycle around for half an hour every day, and then on Monday I hand you a bicycle, it's not going to go well. You need to actually do it on your own to have gotten anywhere. Go do the homework. Send me some of your work if you want me to let you know how you did. You got my number. Okay, I'll stop talking. I'm rambling. Have a good one. See you tomorrow.